now, virtually programming. VirtuallyProgramming.com.
Okay, so finally we get to Blinn-Phong shading now that we've covered garage shading. Garage shading is the foundation for Blinn-Phong, or for Phong shading, both. So we'll see that here shortly. Phong shading, or the Phong reflection model, was developed by, I can't say his name, Blinn-Phong. I don't know how to pronounce that. And was published in his 1973 PhD dissertation. Basically, all it is specular highlights. It adds a specular highlight to garage shading. It could be done on flat shading. It could be done on garage shading, smooth shading, either one. But all it really is a specular highlight, and we'll take a look at that. So here we've got Professor Zombie again, and I don't know if you can notice this difference, but you should see, like, look at, let's see if I can kind of get it centered. Look at his chest there as I turn. You should kind of be able to see like a light reflecting off his chest. He should look somewhat shiny. And part of the reason, this is, first of all, maybe not the best model to demonstrate specular highlights. And second of all, to really see the specular highlights well, I think it would probably help if you could rotate the model, which this is not set up to rotate the model. All it's doing is rotating the camera, so the camera will rotate completely around the model, but the model's standing still, and so the reflection kind of reflects off in the exact same direction no matter what. You can pretty much see it on the chest there, but it's also kind of blowing out. Some of these areas are already almost white, and then you add in the specular highlight of white, and it just kind of blows out to make the whole area just completely white. I think you can kind of maybe see it a little bit better there. Anyway, that's all that Phong is that specular highlight. And where should we go with this? I would almost want to go to the specular highlight value and show kind of how it can be different. We'll do that real quick. Play with this value here. This is basically the amount of specular highlight, and now it's really blowing out that whole area. The specular highlight, the spots, is getting a lot bigger as that number gets smaller, to the point that the light's just kind of almost blindingly big. What if I go in the exact opposite direction? This light, or the model, is so bright that you don't see it. What if I can see it in the eyes? No, not really. The light becomes more dull. I think it gets smaller, but it starts looking more dull and more like flat finished as that spot gets bigger. Let's start out with just one here and see where that puts us. Okay, so there's one. 2, 3. Spot's getting smaller. 4. On a lot of models, you can really see the specular highlight. And then it makes it look almost metallic or plastic or something, and it looks really glossy. The spot just keeps getting smaller the bigger that number gets. Anyway, the spot's almost getting too small at that point. Maybe like a 3.4 or something. And then we'll just leave it there. Yeah, that looks pretty good. Okay, so getting into the Phong shader. This shader was basically created so that you could make objects look shiny. You could make them look kind of more plastic, shiny plastic, or shiny metal, and it helped kind of create the illusion of a light source. I mean, you tend to line up the direction of the specular light with the direction of the diffuse light, so it appears to be coming from the same source. Again, we have the same parameters, the world view and projection matrices. This works exactly like garage shading. There's no difference there. Again, this pad value is supposed to be 16 byte aligned, not 16-bit aligned. The only thing new here is the camera position. This is a 3D position stored as a float 4. So that float 4, the fourth value is a W value. It's not used basically. But that's just your XYZ 3D position where the camera is at in the 3D world. I might look at the code here real quickly. This is XNA. It's not DirectX, but the algorithm's the same. It's just how you implement it that is a little bit different in DirectX. Where's it at? Camera is at. That's what I'm actually passing. See, camera position is the parameter, and I'm just setting it to this camera is at, which is a 4D vector, or a float 4 basically. I initialize it all out to 0. I take the view matrix, the camera matrix, and invert it to turn it basically into a world matrix. You have to invert it to get the values out as if you're using a world matrix. And I output that as a matrix, an inverted view matrix. And then I can use the translation parameter on that matrix to get the position stored within that matrix and the X, the Y, the Z coordinates. And I store them in my 4D vector camera at, set the fourth value, the W, just to 1. It's not really used. And then assign that to the parameter. And so that's how that camera is at value, this camera position here, that's how it's fed. It's basically sucking the position value directly out of the view matrix and storing it here as camera position. Everything else, all these other values are exactly the same as they are in garage shading, or smooth shading, or flat shading if we were doing flat shading. The texture, we're still not using textures yet, but I still have to have it so that it matches the other shaders. And then our input, again, is the same as it's been. The output, we're adding a few new values. World space position is probably the big one. This is going to be our output, so we'll look at how that's fed here shortly. And then the normal, I think we had that before. That's the I think the same normal, the vertex normal, and this texture coordinate, I'm not sure why it's not. We're not using the texture coordinates because we're not doing textures. So it comes in as the input, and we pass it to the output, I guess, but it's being ignored. It's not actually being used anywhere. This world space position is the new thing, and notice that we've got more than one texture coordinate register here. I think that probably could have been texture coordinate 1 instead of 2, but it works either way. Let's see. So everything in the technique is the same. We're still compiling with the same names and so on and so forth. The fill mode is unnecessary. We didn't have to specify that. And so everything is really going to start at our Vertex shader function here, which again has same input, same output as a structure. Obviously, some of the values within the structure are a little bit different. Let's see. I think everything up to here is exactly the same that we had before, except the world space position. So we're taking, first of all, we're taking the position that was in the model file and positioning it in the 3D world using the world matrix, outputting that value to a position within the world. And then we're taking that position within the world and passing that as an output parameter to the rasterizer, which is going to interpolate and pass it to the pixel shader. So the reason we're doing that is because this world position gets multiplied in a couple places to become this final 2D position of the vertex on your computer screen. And we want the original 3D position unmodified by the camera or the projection into 2D space. We want just the original position, not the position that was in the model file. Whoops, there's your FBX file. Not the position in the model file, but the position in the 3D scene where it's supposed to be positioned at. We're just going to pass that straight out. And then we've already covered in the garage shading the normal here. We've already talked about that. If we had a vertex color, we just pass it straight on to the pixel shader. And then here, I guess I'm passing the UV coordinates of the texture to the pixel shader, but I'm pretty certain it's not actually using them. I'm just passing them through for no reason, since we're not doing textures. But then again, there's no real reason to have it in the vertex either. If you weren't interested in doing texturing, you would take those things out because they're just not needed. But we're kind of working up to doing texturing here. And sometimes you might not want to use texturing. You can use vertex colors or whatever, especially if you're going for like an old school look or something. You might not want to use textures. Anyway, so we've covered the vertex shader. It goes through the rasterizer and interpolates values across the face of the triangle to give us each pixel within the triangle, and then passes those pixels one by one, as before in the garage shading. I'm starting to get really hoarse, so forgive me. I'm probably going to have to make this the last video of the day because I'm probably getting laryngitis at this point. Anyway, we've got our parameters much like the last time. We'll cover those as we get to them. Again, we take the direction from the light to the pixel and reverse it so that we have the direction from the pixel to the light. Exact opposite direction. We calculate the vector dot product between that and the pixel's normal, which is the direction the pixel faces, and that gives us a percentage of light between facing into the pixel and facing 90 degrees or more away from the pixel, where here we have the that percentage multiplied times the light color. So you get 100% of that color when it's facing straight into the light, and 0% or black as it faces 90 degrees or more away from the light, and a percentage in between those two angles if the angle between them is between 0 and 90 degrees. And of course, this is all in 3D with 3D vectors. Let's see, this camera direction is new. What are we doing here? Creates a normal that points in the direction from the pixel to the camera. Okay, so we had our camera position, which we pulled straight out of the view matrix, and I looked at that a minute ago. That's a position in 3D space, but we can consider it as a vector. It could be the position of the head of the vector, and we can do vector math on it. So we can take the position of our vertex, which has not been changed by the camera or hasn't been changed by the view or projection matrix. So it's just the place where that vertex is at in the 3D world, passed in through our input structure into the pixel shader here. So we do vector math on those two, vector subtraction, and so it's going to give us a third vector as the answer, which is going to be a vector that points from the pixel to the camera, which this was the pixel. Yeah, because this is the position of the vertex, right? But it's run through the rasterizer to be normalized, so it's actually the position on the face of the triangle for this pixel, because the pixel shader deals with one pixel at a time. So this is actually the 3D position of the pixel, not of the vertex. And so this is the camera position where the camera is at in the 3D world. And so we get this vector that looks from the camera to the pixel that we're actually working on here. And or I'm sorry, the other way around, from the pixel. It's a vector that points from the pixel to the camera, wherever the camera is at, and then we normalize it to make it a vector normal and store it as the camera direction. So it's the direction from the pixel to the camera. So now we know what direction it is when you're going towards the camera. And then we get into the actual Phong specular stuff. There's a little bit of a shortcut here. The diffuse light percentage, if the angle is greater than 90 degrees, the diffuse light percentage is 0. And so we can just go ahead and set this to black. We never want a specular highlight shining in the shadows, basically. And so this is a shortcut, a short circuit, if you will, that avoids this big long calculation and just says, hey, we know at this point it's going to be black. There's no point in calculating it. Just set it to black and go on. So if it's less than 90 degrees, if it's between facing perfectly into the light and 90 degrees away from the light, then it's going to calculate the Phong specular highlight and put that as a color for this pixel, which will then be combined with the ambient light color and the diffuse light color to make one color for the pixel. And you've basically just covered Phong shading and the specular highlight. But obviously we want to look into this a little bit more. We're passing 5 values. This is actually a function. See, you can add functions in HLSL. You don't have to just have the pixel shader and the vertex shader. You can make your own functions to kind of make the code more readable. I mean, you theoretically could have put this in the pixel shader rather than separating it out, but it just makes the code more readable as a function here. We had to find 3 new variables that we'll talk about as we get to them here, but the input parameters are the light direction, the light color, the pixel normal, the camera direction, the camera direction, and the specular power. And let's look at the input there so that we get a matchup. The light direction was the direction, well, maybe it's time to look at our drawing here. I made this drawing for you that kind of explains all this and how it's actually done. Basically, you have the camera where, you know, that's where you're going to draw from. That's what's seeing this. And camera's over here someplace, and we've got this object here, but we're only looking at one single pixel in the pixel shader. And that pixel faces a specific direction, which is the pixel normal here. And the light, or diffuse light source, shines in a particular direction towards the pixel. And if you reverse that, it actually goes in the opposite direction, which we did. And then the diffuse light reflects off at some angle. Well, if you study physics, you find out that when light reflects off a surface, it deflects or leaves the surface at the exact same angle it hit at. So if it's straight down, it's going to come straight back up. If it's off at some angle here, it's going to hit and then reflect off, so that that angle is exactly the same when it leaves as when it hits. So in the bottom picture here, we've got the same thing. This is the exact same vectors that we had up here, but it's written out a little bit more mathematical here. And so the blue vector is the reflection vector. The yellow vector is the direction to the light source. And the angle between the reflection vector and the pixel normal is going to be the exact same angle as between the light direction normal and the pixel normal. It's just two opposite directions, but the angle on both sides is exactly the same, and I've represented it with the Greek letter theta. So theta is just the angle between, or those two angles from the normal to the vector, or from the pixel normal to whichever vector we're talking about here. And so if you think about it, the specular highlight is going to show up when the camera moves to a position so that it's in the path of the reflected light. So if your camera is looking straight down the path of the reflected light, you'll see the reflected light. If it's way off to the side, you're not going to see the reflected light because you're not in the path of the reflected light. And so as you get closer and closer to that path of the reflected light, you get more and more of that specular highlight. And that's the way this whole thing works. To go into that in a little bit more detail on how it works, this gets really math intensive. It's a lot of trigonometry here and some algebra. I'm going to attempt to explain this drawing here. This is the math behind the specular highlight of Phong shading. Down at the bottom, I have the formula that you'll actually see in the source code. Let's see if I can highlight that. Yeah, this code right here is what is actually in the source code for the HLSL shader. That's the exact code. And it reads reflected light direction equals 2 times the pixel normal times the saturation of the dot product between the pixel normal and the light direction normal minus the light direction. And all of the math here on the screen is here to explain that. You'll also notice that this formula right here is the exact same thing written out as a math equation rather than as source code. But if you compare the two, it's saying the same thing. And all this other math is working towards that. So it all kind of starts here with that drawing, or that part of the drawing. That is representative of this portion of this drawing, which is also essentially the same thing as this portion of this drawing. We're just not including the right hand side, which is the S2 side. Over here you have an S2 equation. Over here we have an S1 equation, and so this is just concentrating on the S1 equation. I could actually name that S1 if I could write a subscript for 1 right there. But this drawing is basically explaining this equation. So we have our pixel normal here, and any normal by definition has a length of 1. So this is just an arrow that describes what direction our pixel is facing, that has a length of 1. And we're really trying to figure out this S2 value here, and ultimately the R value, which is the reflected light direction, for this equation here. But we need that S2 value to get the R value. So we got to work through all this. This is a lot of vector math. It's related to trigonometry, but I mean, obviously with cosine and whatnot, there's some trig here, but it's really mostly a vector thing. Here with all these arrows, the way it's lined out, I'm kind of making a right triangle here, but these are actually vectors, and so don't get confused by that. So we have our vector here, which we're trying to make a right triangle out of these vectors, and we start out with this being the normal here. Whoops. Let's try circling that again. The tablet I'm drawing with doesn't allow me to do things very accurately. The stylus is not working for some reason, and so I'm having to just draw this with my finger, and it's not working out very well. Anyway, this normal becomes this vector in order to make this right triangle. And whatever length it has, it's going to be shorter than this, because the L vector and the N vector are both normals. They both have a length of 1. They have, which means they're the same length. And so this is really going to be more like that, actually. But in order to form a right triangle here, we need to shorten this to whatever length. And cosine theta is going to, not in cosine theta, but cosine theta is going to give us that length of that vector. Because as I covered in a previous video, when you have a vector dot product between two normals, you basically get the cosine of the angle. And so that's going to give values between 1 and 0 as a floating point number, which is basically going to be a percentage. So when the two vectors are on top of one another, like just take any vector as an example, if I can draw a straight line, which I can't, but you know, if our vector was on top of the other vector, completely on top of it, the value of cosine theta, or the dot product between the two vectors, would be 1, I believe. And if it's greater than, or if it's 90 degrees or greater from the vector, then the dot product between the two vectors, or the cosine of the angle, will be 0. So if it's if the difference between the two, let's see if I can write this way. If they're on top of each other and the difference between the two is 0 degrees, then the value is going to be 1.0. This is ridiculously difficult to draw this way with this graphics tablet, so forgive me. And then if it's 90 degrees, that's supposed to be 90 degrees. And this is supposed to be an equal sign. That's a terrible equal sign. Then it's going to be 0. And I already covered this in a previous video, but whatever the angle theta is between the two vectors, it'll give you some number between 0 and 1, and that will give you a comparison to the angle. If it's 90 degrees or greater, it's going to be 0. So all of that is cosine theta here. And that value, when you multiply a vector such as n, which is n is actually this vector here, not the one here. But when you multiply this vector here, the pixel normal, times a scalar value, any normal times a scalar value is going to change the length of that arrow, the length of that vector, to be that value. So if cosine theta here, if that calculation of the dot product, which is actually going to be the dot product here, if that dot product between the pixel normal and the light direction normal, which are this normal and the yellow normal, or it's also the pixel normal here and the direction to the light normal there. When the dot product between those two, or whatever the dot product between those two is, it'll give us a percentage between 0 degrees on top of one another and 90 degrees, or a right angle, and any value in between, it'll give us a percentage between those two values. And so it just becomes a percentage, and when you multiply it times this n vector, it'll change the length of the n vector to be according to that angle. And so if you imagine the light vector being a 90 degrees away, pointing out here instead of where it's pointing, then that s vector, the s line here, is going to be on top of it, pointing in the opposite direction. And so its length would be the length of L, which the L vector, the light vector, which would be 1 because it's a normal. And so actually, I think I had that backwards. 90 degrees is actually 1.0. And then as that L vector comes to match up and be on top of the n vector, then this s here would have a length of 0 because the two are on top of each other, so there wouldn't be any way you could draw a line between them. And then when it's some place in between, which it is in this drawing, then this is going to have some length. The s vector is going to have some length, which is basically an unknown. We're trying to figure out what it is here. But we know this vector, which is has a length of 1, we know that, and we know the original pixel normal had a length of 1, and we know that if we take that normal and multiply it times the dot product here, n dot L, it'll give us some value, which say this is 30%. We'll say that this is this angle here, or the angle here, represented by theta, is 30%. So that would give you 0.3 for that dot product value, which is basically 30% of the possibility there. It's basically going to take this normal here, this pixel normal, and shorten it to be 30% of its previous length, or it will then take on a length of 0.3. So then this whole thing here, n times cosine theta, is basically just saying change the length of the pixel normal to be whatever the angle there is. So if it's 30% of the way between 0 and 90 degrees, then the pixel normal will face in the same direction, but it'll only have 30% of the original length. But any way you look at it, it's going to change this pixel normal arrow here to point in the same direction, but have a new length, which basically makes this a right triangle. And it'll have the correct length at that point, whatever it is, in order to make that into a right triangle. And so you could really kind of think of this n cosine theta as its own value. Like if you were to set it, if you were to say that all of that, our new normal, becomes x. It's not a very good x. Then you could replace that here in this equation to become x minus L. Let's write that, if I can write it halfway decently here. X minus L equals S1, S sub 1. It's very hard to write with this tablet. Anyway, so x there is this vector, which is not a normal because it has a length that's not 1, and minus the L vector, which is a normal and does have a length of 1. And so this is just vector subtraction. If you go back and look at my vector videos, maybe I shouldn't have erased all that. Edit, redo. Keep that formula on the board for now. So we're trying to calculate this S1 value. We want to know this vector. So that's vector math. We're just basically taking the x vector here and the L vector, which happens to be a normal here, and doing vector subtraction on it, x minus L, that's vector subtraction, and that will give us as an answer a vector which is not normalized also, which is the S vector. And it just says looking, what direction is it looking from the L vector to the N vector, and how far is it? And that value is our S vector there. And you can look in this drawing and see that the S vector of S1 and the S vector of S2 are identical vectors. It's the same vector as shown in this drawing here. And so that makes the left side of the equation equal to the right side of the equation, which is what this is explaining, that they're the same vector, so you can treat them mathematically as the same vector. And so this S2, we have S2 as a given. We know, once we know what S1 is, which we calculated here, then we can know what the S2 vector is from this equation. And that gives us another right triangle here from that side, and that side. And we already know this side because of this vector here is going to be x, or n cosine theta, which is what we have here, n cosine theta. This could also be rewritten as s sub 2, if I can write a sub 2. That's a big sub 2. Equals the r vector minus the x vector. Again, this is all vector subtraction. And if you don't know about vector subtraction, watch my vector video. But s sub 2 equals the r vector minus the, I'm sorry, not n vector, but x vector, where the x vector is n cosine theta. And so if we look at that, let's see, we're trying to discover this vector here, r vector. This is the direction of the reflected light. When the light comes from the diffused source and hits the pixel, it should leave at the exact same angle, which should be the direction that the r vector points in. So that's what we're trying to calculate here. Is we want to know where that reflected light is going. So we want this normal here that points in the direction of the light being reflected off the surface. And so we know the x vector here, and we know the s2 vector here because we calculated it as the s1 vector. And so if we subtract from, let's see, trying to make this the short version like it is here. If we subtract the actually this equation's probably written kind of funky. It's saying that this S2 is equal to taking the r vector here and subtracting the x vector, which is true. It's a true statement. It would give us the S2, but we have the S2, and we need basically to rewrite that. So anyway, we can rewrite this s sub 2 equals r minus x, which we can geometrically see is true, as s sub 2 equals the r vector minus n cosine theta, because that was that's what x is. X is n cosine theta. And because s1 is equal to s2, then we can take this equation and substitute it for s2 here, and we can take this equation and substitute it for s1, and then this becomes a geometrical proof for this down here. So if you do a little bit of algebra, you should be able to simplify this equation down to this. We're trying to solve for r. We want to know that reflected light direction, that vector. So we're trying to get that vector there. And let's see. So we want to set, we're solving for r, so we want to take everything other than r on this side of the equation and move it over to this side of the equation. And so if we add n cosine theta to both sides of the equation, then this negative n cosine theta would be canceled out by adding a positive cosine theta, and we would have on this side we'd have n cosine theta. Can I write cosine theta? Not very well. I can't. This graphics tablet is ridiculously difficult to write with. Cosine theta. Oh, that's a huge theta. Anyway, we'd have n cosine theta plus n cosine theta here minus L, which you could take n cosine theta plus n cosine theta and turn that into 2 times n cosine theta, which is what we have there, and then that would be minus L. So if you just work through the algebra there, you can turn this equation, if I can circle it, you can turn this equation into this equation using algebra. And then again, we know that the cosine of the angle is the same as the dot product between two normals. And so we can take our cosine theta here and substitute in, using algebra, n dot L, the dot product between the two vectors, which is what we have here. The only difference between this equation and this equation is that we substituted in the dot product between the two normals for cosine theta. And once you get here, then you have the exact same thing that you have here. And so you've basically proven this entire drawing. And let's see, clear everything here. And so ultimately what we're actually solving is for this v vector here, which is actually not in the code here. And we're trying to, the v vector being the view angle or the camera, that's from the pixel to the camera, direction from the pixel to the camera represented by that normal. And we're actually going to compare that with the reflected light direction here, and we're going to do another dot product right after this to get to compare the two, which will actually be the angle alpha here. And by doing another dot product between R and V, we can calculate the angle between them, and that way ultimately what we're doing here is comparing the direction of the camera and the direction of the reflection, so that if the camera is aligned with the reflection, and say the camera were here looking this way towards the pixel, then they would be perfectly aligned, and we would get the full light from the reflection here. But as they become less and less aligned, because this angle alpha here becomes greater and greater, then you get less and less percentage of this reflected light, which is also controlled by the specular power, which determines the fall off and how quickly, as the angle increases, how quickly the light falls off or turns to darkness. Well, anyway, yeah, that's basically what we're doing there. We're getting this. We're trying to calculate this reflected vector here and find out what that vector is. And so through going through all this math, we can calculate the value of the reflected vector, which is going to be the pixel normal vector times 2 with a percentage between 0 and 1. You know what I think that is? I think 1 times the pixel vector is actually right there, like we talked about. 2 times is actually twice the length and points out all the way out here. And so that minus L, oh boy. I'm really having to think this through. Let's see. Yeah, that minus the L vector creates that vector. Is that right? I always get vector subtraction backwards. So it's probably going to give us that vector, which, looking at it geometrically, the rules of geometry say that those two vectors are identical. The R vector and then this vector that we just calculated here are going to be the exact same vector because they point in the same direction and they have the same length. Because L is a normalized vector, it has a length of 1. R has a vector of length of 1. Yeah, that even works in 3D. So if you think about it, wherever this L vector is pointed to, it's going to be pointed towards the light, and wherever this N is pointed to, it's going to be twice the length of the pixel normal, but it's going to be, or the pixel direction, it's going to be twice the length of the X vector, but it's going to be pointing in the direction that the pixel's pointed in, and when you do vector subtraction to get a vector that points from the light source direction to the pixel normal, it's going to be the exact same vector as this reflection vector. Wow, that's unbelievably ugly, but it is what it is. This is, I guess the Phong guy was pretty smart, huh? He figured out how to calculate the specular reflection based on this. And then the next thing we are going to do is look for this angle alpha with the Greek letter alpha here between the reflected vector and the view matrix vector, the camera vector. So this is going to point from our pixel to the camera and then our reflection vector. So all of this was to calculate the reflected light direction vector right there, right? Which is the R vector here, and gives us a normalized vector. I think it should be a length of 1 normalized there, that points in the direction of the reflection, and then we can figure out whether the camera is looking down that path of the reflection or not. Oh boy. So all the way back to the HLSL code. We have the Phong specular function here. We passed in all these values. I just explained all this code. It took a lot of ugly math, trigonometry, and vector math to explain that one line of code. But that's why this one line of code works, and it gives us a vector, which is the direction of the reflected light. And we take that and we do the vector dot product trick again with that camera direction, the view matrix direction vector here. We need that angle alpha there, and we use the dot product trick to get a percentage between 0 and 90 degrees, and we saturate it so it doesn't go over 100%. And then what do we do next? I'm trying to figure out how this works. So we've got this angle as the dot product, and it's a percentage, 0 to 100%. We could just make that the specular highlight amount, right? We could just say, okay, it's going to be 100%. That's the amount of light we get. But we allow you to specify the specular power, which is an exponent. It gets what do you say? It gets not multiplied, but it's taken to that power. So if this were 2, it would be 1, which is 100%. It'd be 1 to the second power, which would still be 1. If it were 4, it'd be 1 to the fourth power, which would be 1, because it'd be 1 times 1 times 1 times 1. So whatever it is if it's 100%, if you're straight down the path of the light, the specular highlight amount, regardless of the power, is going to be all of it. It's going to be 100%. But it's going to work in the opposite way, so that the smaller the specular highlight gets, the greater it falls off. I think it falls off faster. So yeah, that's this is what determines the size of the specular highlight, because you've got this dot of light that is shining from the light source, from the path of the light, and you're looking straight into it, so you're seeing the exact light. And as pixels move away from that exact reflection point, they're going to not have the perfect angle to look right into the light and reflect it off to the camera. And so as it gets further from that spot, the specular power here will apply less and less. So it's not, this is actually, I think, doing a root. What do you call that? It could be, like, if it were 2, it'd be a square root. If it were 3, it would be doing a cubed root. And I think that's actually because, wow, this gets into some ugly math here. I believe that taking a number to the 1/2 power is the square root. So if you've got, I think 4 to the 1/2 power is the same as 4 squared, which would be 2. And 9 to the 1/3 power, I believe, would be the cubed root of 9, which would be 3. This gets into some kind of ugly math. So if I'm right about all that, basically it's just saying that the specular highlight is going to fall off faster and faster, or it's the speed at which the specular highlight falls off at, or in more plain English, it's going to be the size of the specular dot. And the greater this number, I believe, the more it's going to be like a root. It says power here, but I think the way it calculates out is more and more of a root. We could play with that value a little bit. What do we get if we go 0.1? It doesn't hardly fall off at all, although it does look really shiny there. And what did we get at 1? See, I think when we go to below 1, we're basically doing like roots instead of powers. That does, yeah. Okay, it does look a lot more metallic now, and yeah, I think this is actually the way it's supposed to work. Looks more metallic. You can really see the specular highlight, although it's the angle and everything, it's really kind of blowing it out. I think this model may not necessarily be the best model for this. If I keep adding zeros, will it keep getting more and more shiny? Feels like that light source is getting a lot bigger, but yeah, it does seem like it's kind of getting more shiny, more metallic as I add zeros. Part of the problem, though, is that it's, yeah, wow, really blown out at that point. It's the specular highlight dot is so big at that point. I don't know, that still looks pretty much like when it had all the additional zeros. But anyway, that is the specular value. Let's see, find the shader code again. Yeah, that's that specular power. We're passing it in here, and it's just taking the angle between the reflected light and the camera, and according to whatever number you set the specular power at, it's going to give it a percentage of that specular light, so that the specular power determines the fall off. It determines how quickly, how big that specular spot is. And then the specular light is a float 4. It's going to be the return value. It's going to be the color of that pixel. So the question, what this function is trying to determine, is whether this pixel should reflect the specular light. And if it should fully reflect it, then it's going to return this color of the specular light. So this would basically be like 100% for the specular highlight amount. And then you take the light color, which is the main light source, the diffuse light color, and whatever that color is, you apply the specular highlight amount, so that it's basically going to be black, no color, or the specular light color here will basically be black if the angle is greater than 90 degrees, and you'll get the light color lighting up the pixel if the specular light is reflecting off that pixel. Hopefully that makes sense, but that's all there is to Phong shading, because that specular value is stored, or is returned as specular color here, and it's simply added to the other colors for the pixel, and that's the entire Phong shader. That's the whole thing. That's Phong shading right there. And now you can maybe see why we shortcut this value, where you're saying, hey, if it's greater than 90 degrees, we know it's not going to get any specular color, so don't go through all those crazy calculations. Just set the color to black and go on, which should save a significant amount of time in the shader. Plus, I think there actually may be a divide by zero error or something in the shader. Let's try removing it. I think it'll blow up, because I think there's like a divide by zero error or something. Let's try it. Oh no. In fact, actually, I think that actually looks better. That's really sad that I'm just figuring that out. Well, the other runs faster. So let's play with this a bit. Okay, that's getting kind of a duller. You can kind of see it on the chest there. Yeah, that's getting a lot duller. But I'm kind of thinking this actually looks better. But it's running the specular calculation, which is an ugly calculation, as you just saw, for everything here. So let's just set that to something like that. Yeah, other models, you'll actually, the specular highlight will probably look better on other models. And it also depends on the angle between the model and the light, which is not changing here. The model is fixed, position, fixed. The model doesn't rotate. I'm rotating the camera around the model, even though it's hard to tell that. And so you might be able to get to demonstrate how shiny it is a lot better if you rotated the model instead of rotating the camera. So that is Phong shading. That's everything to it, and you can see how it builds on some of the other shaders. I've got enough of a hoarse throat. I think I may stop recording here today, but hopefully I'll have the Blinn shader, which is the Blinn-Phong shader, out pretty soon. And it's basically the same as the Phong shader. It's not significantly different. It's the same thing, but there's a shortcut in the calculations. And so we saw how ugly the calculation was here. Blinn introduces a shortcut into the specular calculation to make it a little bit simpler. And because it's a slightly different way that it calculates it, the results look slightly different too. So we'll get into that in the next video.